quantum physics has revealed that matter and light can have a particle and a wave-like character at once. Atoms, which are usually described as discrete entities, can also behave as matter waves, and light, which is usually described as an electromagnetic wave, is made of single particle, discrete particles, the photons. This duality has led to a strange world in which atoms and light fields can exist in state superposition, so to speak, suspended between different classical realities. The fathers of quantum physics, which have discovered these laws by observing properties of matter and radiation which could not be explained by classical physics, were not able, at the time they were founding the theory, to observe directly this strange behavior on particles of light or matter. So they imagined thought experiments. For instance, Bohr and Einstein, in their discussions, imagined that they would be able to trap single particles, for instance, single photons. You see here the famous photon box that Bohr drew when discussing with Einstein, in which a photon would be stored and then released on demand through this shutter. And you see that the experiment was not real, but Bohr drew it with exquisite precision. And you see that there is a clock here which plays an important role in the experiment. I will come back to this later. But at the time they were thinking about these experiments, Einstein, Bohr, and Schrödinger did not believe that such experiments would one day become possible. Of course, they knew, and Schrödinger knew in the 1950s, that single particles could be detected. But the detection occurred by destroying the particles. You see here an example of the traces in a bubble chamber. Also in accelerators, when particles collide, you see the debris of the collision after the particle has been destroyed. So, in fact, it was post-mortem physics. The objects were destroyed while being observed. And Schrödinger put it in a very nice way when he said, it is fair to state that we are not experimenting with single particles any more that we can raise ichthyosauria, I'm not sure I pronounce correctly, in the zoo. We are scrutinizing records of events long after they have happened. So particles exist, but it's difficult to have them in a zoo. But things have changed since then, and now we are performing these thought experiments. They have become real, and we can control a zoo of particles, tame them, and observe them. And this has become possible due to the development of new quantum technology. First of all, tunable lasers, which allow us to explore with very high precision the structure of atoms and also to manipulate atoms. You also need fast computers to analyze the data and to take in real time the data provided by the experiments. And in some cases, you need also superconducting technology to have mirrors which will hold the photons, the particle of light, long enough. And I think it is interesting to note that these technological inventions are all born from quantum physics. So it's a very nice circle which is closing here. From quantum theory, you get quantum technology, which enables us now to demonstrate directly the strangeness of the quantum world. So many experimentalists in the world are now working in this field called quantum optics or quantum information, and they are able to tame this particle in the real world. This year, Swedish Academy of Sciences, as we just heard, has decided to put this field forward by giving the prize, the Nobel Prize in Physics, to David Weinman and myself. But I am sure he agrees with me that we are just here as representatives. We are representing a very wide field of physicists, and I am very glad to see that many of them working in labs in the world are here today. It has also been pointed out that the experiments that we are doing in Paris and the one which are done in Boulder are very similar. They are the two sides of the same coin. While Dave in Boulder is manipulating single atoms with photons, we in Paris manipulate single photons with atoms, and we both do it in vivo, as opposed to the post-mortem physics that we were talking about before. Now, just to show you the analogy between these two kinds of experiments, I will show you two figures which are taken from two papers which have been published back-to-back in 1996. In our group in Paris, we detected the signature of an atom oscillating, an atom coupled to an oscillating electromagnetic field in a trap. And at the same time, in Boulder, Dave groups was observing the same signature from an ion oscillating in his trap. Technically, these oscillations are called Rabi oscillations, but you don't have to know anything about them to recognize that there is a strong similarity between these two kinds of signals. It is at that time, in 1996, that Dave and I and our wives, Claudine and Sedna, became very good friends. And it turned out that Dave and Sedna came to Europe for a conference, and Claudine and I took this opportunity to distract Dave from his research, not really because we wanted to slow him down in our competition, but because I think we wanted to open them to the pleasures of European and more specifically the French vacation concept, which seems to be absent in the United States. So you see here a picture which was taken in the Boboli Gardens in Florence in August 1996. And this is a testimony of the fact that Dave is not always working. But the story about taming atoms and photons started much before. And Dave will tell you about his part of the story. I will tell you about mine, which started in the 1960s. I performed my PhD thesis with Claude Cohen-Tanucci, and I was working at that time on optical pumping experiments, learning that lasers could be used to manipulate atoms, and also on the dressed atom formalism, which is a formalism which quantize electromagnetic field to understand better its interaction with matter. And I remember that on my thesis committee, one member of the committee, Anatola Bragam, who has a very abrasive mind, asked me, why do you quantize the field? You are working with classical fields. You have zillions of photons. You don't need to do that. I don't remember what I answered to him, but in retrospect, I could have told him, one day, sir, I will be working with a single photon, and then I would need this dressed atom approach. After my thesis, I went for a postdoc with Arthur Shallow in 92-93, and then I learned to work with dye lasers, which were developing there, and I did quantum bit studies. Quantum bits involve exciting atoms and looking at the time evolution of state superposition. So I started at that time to work on this concept of state superposition. I just want to mention that these two gentlemen got the Nobel Prize in Physics in the year 97-81, and I remember that 15 years ago I was in this room but on the other side of the stage, and I am very moved to see that Claude is here today and that we exchange our roles. So it's very nice. So but the story really started sometime later in the 1970s when I came back from Stanford, and I started to use dye lasers to excite Rydberg atoms, very excited atomic states. And you know, this week in Sweden is full of surprises. I just met a few minutes ago the grandson of Rydberg, who is attending to this lecture, so I'm very pleased about that. So Rydberg gave the formula which explains the physical the spectrum of these states, and we start to investigate them with our system, which was very simple. We had an atomic beam which was crossed by lasers, tunable lasers, and we were exciting Rydberg atoms. And at the same time, we were irradiating these atoms with microwaves, which were confined in an open cavity made of copper mirrors. And so we're looking at the microwave absorption, to which these atoms are exceedingly sensitive. So we're very interested in this very high sensitivity. After the atom left the cavity, they went in this zone where they were ionized between two condenser plates, and they were ionized at different times because the field increased in a ramp. And in this way, we were able to discriminate the signature of the upper and the lower state. And this is a technique that we are using to this day to detect very efficiently Rydberg state and transition between Rydberg states. So when we did that, we observed something which at first was very strange. We saw that if the atom was initially excited, and if the cavity was tuned on resonance, we did not need to apply any microwave. The system was undergoing a fast transition from the upper to the lower state spontaneously, and we recognized that we had built a maser, a transient microwave maser. But what was surprising is that the threshold of this maser was exceedingly low. We had only a few thousand atoms in the sample, as opposed to ordinary laser or maser system, which required billions of atoms. So at the end of the papers that we wrote at that time, we made a comment saying that by increasing the Q factor of the cavity, we could go to very small absolute atom numbers. And in fact, it was the start of our hunt towards single particle physics. And this field, which studies the interaction of atoms with fields within cavities, is now known as cavity quantum electrodynamics. So we kept increasing the Q factor of our cavity, and one way to do it was to go to superconducting mirrors. So we replaced our copper mirrors by superconductive niobium mirror at very low temperature, and then we were indeed able to increase the Q of the cavity and to decrease the threshold up to the point where we got single clicks in our detectors, and we observed the fast transfer of a single atom from the upper to the lower level, and which is the transient regime of a maser, and it's an effect which was predicted by Ed Purcell in 1945. But we still were not satisfied, because the Q of our cavity was not big enough for the field to be able to stay in the cavity long enough to be reabsorbed by the atoms. And what we wanted to realize is this regime of quantum mechanical oscillation between a two-level atom and a single field mode, which is called now the strong coupling regime of cavity QED. So we went on a hunt to get to the strong coupling regime, which became our holy grail. And we tried to improve the cavity factor. So it was a very exciting time in our lab, and I found a few pictures of this time. This is me with my first two graduate students, Michel Gross and Claude Fab, back to the camera in our office. And here you see Philippe Gouat, who is a specialist of solid-state physicist who was working in next lab, and who is a wizard in microwave technology. And he developed all the microwave sources and microwave analyzers that we use up to this day. So his collaboration has been essential to the success of our work. On this last picture, you see facing me, here you have Claude Fab and Kaluzny, and facing me, Jean-Michel Raymond, I think in 1980. And I'm glad that we stayed together and worked on the same project since then. So we were at a loss to increase the Q of our cavity at that time. Niobium was fine as a superconductor, but it's a very poor material to be machined, and so the surface of our mirrors were not smooth enough, and the photons were scattered out. And so we were trying to do something better when we heard from Munich that Herbert Walter has succeeded to reach our holy grail, getting into the strong coupling regime of cavity QED. And so he achieved that before us, and it was, at the same time, we were very admirative of his work, but we were a little bit worried that we were behind. In fact, he had a very bright idea with his student Dieter Meschede. He replaced the open cavity by a closed cylinder, and then the quality of the inner surface does not matter anymore, and he could increase the photon lifetime in his cavities by 2 to 3 orders of magnitude. And what they built is a micromaser, a device where atoms go through the cavity one by one, and a field builds up in a cavity in a steady state. This micromaser physics has been very successful in the 1980s and 1990s. And Dieter Meschede became a postdoc of mine during the few years I was working part-time at Yale University. And then he came back and became a professor in Bonn, and he's doing now very beautiful experiments on cold atoms and quantum information, and we have been exchanging students and postdocs over the years, and it has been a very fruitful collaboration. But so we witnessed these developments, and we wondered whether we should go to closed cavities. But we still decided it was better to stick to open cavities because this closed cavity had a problem. The photon lifetime is very long, but you see that the atoms have to get very close to the surface of the metal because they have to go through very small holes. And the atomic superpositions are very sensitive to stray electric fields close to the holes. So in this experiment, it's very difficult to control the atomic state and hence the field inside. So we decided we really had to go on with our open cavities. And it took us about 20 years to develop the technology which enabled us to get open cavity with the same kind of Q as these ones. So, and this led us to the experiments which bring me here today. But to describe these experiments, I think I will switch from the historical description to something which will be more deductive and emphasizing the physics rather than history. But I have to start with the first point. Usually when you talk about detecting light, you use the photoelectric effect. And the photoelectric effect, which was described first by Einstein in 1905, destroys the photons. What you have when photons impinge on a sensitive detector, your retina or a photosensitive cathode, you get clicks which shows that the photons have been there, but the click destroys the photons. So you had a photon, and after the click, you have 0 photons. The photon is gone. So this is not so much different from the brute force experiments I described to you before. In fact, what you're observing with your eyes or with any kind of detector are the debris of collisions of the photon with a photosensitive surface. And this is not what you want if you want to detect photons in vivo. What you want instead is a situation where one click leaves you the photon inside your system, and so that you would be able to repeat the experiments again and again. And this is called a quantum non-demolition measurement, and it was pioneered, the theory of this kind of experiment was pioneered by Vladimir Braginsky back in the 1970s. But to achieve that, you need two ingredients. You need first a non-demolition detector which works without absorbing the photon, but which is sensitive at a single photon level. And you also need a very good box to keep the photons long enough. And so we are back to the photon box that I discussed in the thought experiment of Einstein and Bohr. And the photon box we came upon is shown here. In fact, what we did during these 20 years was to improve the surface of our mirrors. And the Q of the cavity increased progressively. It went into the 100 microsecond domain in the 1990s, which allowed us to do some experiments. And then in the hundreds of milliseconds in the years 2000. And the final idea was to use mirrors, spherical mirrors, made out of copper, because copper can be machined very precisely. And on this copper surface, we sputtered a little bit of niobium. So we took advantage of the mechanical quality of copper and the electrical quality of niobium. And then we were able to get mirrors on which light can bounce more than 1 billion times, making a folded journey for the photon of 40,000 kilometers, and giving a lifetime of 130 milliseconds to the photon, which allows many atoms to cross the cavity one by one, to extract information from the cavity field, and to perform experiments in which we control the photons in vivo inside the cavity. But of course, for that we need special atoms. And the second point is what kind of atom we are using. We use Rydberg atoms, and here is a picture of Rydberg, but we use special Rydberg atoms called circular ones. A circular Rydberg atom is an atom in which, by a succession of laser and radio frequency excitation, you promote one electron to a very large circular orbit, which is 1,000 times bigger than the orbit of the ground state. The technologies that we used for doing this kind of experiment was following the ideas of Dan Kleppner, who developed it in 1983. And I want here to acknowledge Dan's importance for this physics, not only because of his impact on Rydberg atom physics, but also because he was very important at the beginning of cavity QED. And for instance, he performed experiments on the inhibition of spontaneous emission between mirrors. And I think that at the beginning of cavity QED, the microwave domain, both Dan Kleppner and Herbert Walter, who sadly died in 2006, have been really pioneers, and I think they should be acknowledged both in this context. If you want to understand how this atom behaves, you have to remember that electrons are also waves, and so what you have is a de Broglie wave going around the circle, and the principal quantum number of this excited state is just the integer number of waves which can be put inside the circular orbit. And each of these eigenstate, energy eigenstate, has a circular wave going around, which is completely delocalized. You have the same density all around, which means that the system has no electric dipole. But if you want to couple to light, you need an electric dipole. And the way to get an electric dipole is to go into state superpositions. If a pulse of microwave realizes a superposition of two adjacent states with principal quantum number 51 and 50, you prepare a superposition of these two states, which, if you wish, you could call a Schrödinger kitten. It's like Schrödinger's cat, which is suspended between life and death, states E and G, but of course a very small cat because it's just a single particle. So we can prepare this kind of systems, and when you do that, the two waves, which have 50 and 51 nodes, interfere constructively at one end of the orbit and destructively at the other end, and now you get a big dipole rotating at 51 gigahertz. This dipole is like the hand of a clock. And in fact, what we have built here is, what we are doing here is the building of a Rydberg clock, which is ticking at 51 gigahertz. And we will use this clock to measure light non-destructively. The important point is that the atom will be slightly detuned from the cavity so that the photons will not be absorbed or emitted in the cavity, but still there will be an effect. And this brings me back to the contribution of Claude, who discovered in 1961 that non-resonant light modifies slightly the energy level. These are the light shifts which have had a tremendous importance in all kinds of atomic physics and quantum optics experiments during the last 30 years. In our field, what happens is that when the atom crosses the cavity, the energy levels are slightly shifted upwards and downwards, which means that the phase accumulation of the atom going between the mirrors is different depending upon the intensity of the field. And the effect is so sensitive that you can get a phase shift per photon phi naught as large as pi, 180 degrees. This means that whether you have 0 or 1 photon in the cavity, the dipole will point in one direction or in the opposite direction. And if you are able to measure the phase of this dipole, you will count photons without destroying them. Of course, if you want to measure a phase, you need an interferometer. So we built around our cavity an interferometer which is made of two auxiliary microwave zones, R1 and R2, in which we apply pulses of microwave before the atom enters the cavity and after the atom leaves the cavity. The first pulse prepares a state superposition which starts ticking, and the second pulse is a flash of microwave which allows us to analyze the phase of the superposition. This succession of time-resolved pulses is known as a Ramsey interferometer. It was introduced by Ramsey in 1949, and it became the standard device of atomic clocks. I know that Ramsey was Dave Wineland's PhD advisor, so you see that our story is entangled in many ways. So we use this setup, and with this setup, we were able to detect single photons. In fact, if you have a phase shift of pi per photon, what the second Ramsey zone does is to map the two dipole states which are opposite into states E and G, which are finally detected in the detector. And you get, so what we have built is an atomic clock which is delayed by the photons which are trapped inside the clock. I am a little bit ashamed to talk to you about an atomic clock which has an accuracy of 10⁻⁷, because Dave will talk about clocks which have an accuracy of 10⁻17. But his clocks are, I must say, insensitive to light, which is not interesting us. We want to have a clock which is very sensitive to light, and so we use Rydberg atoms. So you see here the kind of signal. A blue bar means an atom in level G, a red bar an atom in level E, and you see in real time the kind of observation we get. And when we got for the first time this signal, we were really very excited. You see here that you have a jump here it means that you have 0 photon in the cavity, 1 photon, and then back 0 photon. And this photon is just a black body photon. The cavity is very cold, and from time to time, due to Planck's law, 1 photon pops in the cavity and goes out, and we measure this. And we see exactly the time when the quantum jump, the sudden change of the light field occurs here. These quantum jumps, by the way, were predicted by quantum theory long ago, but in spite of that, people like Schrödinger didn't believe in them. The quotation I gave you in the beginning comes from an article whose title is very speaking for him itself. He says, are they quantum jumps? So these are quantum jumps observed with light, and Dave will show you in his talk quantum jumps occurring in single ions, which had been observed 20 years before we did our experiment on light. But this was the first time the quantum jumps were observed on light. You see also that hundreds of atoms see the same photon. The atoms cross the cavity one by one, and they all agree that there is a photon inside, so it's really non-destructive. We could extend also this experiment to measure higher photon numbers. Then, of course, a single atom is not enough. You have to send a sequence of atoms, and each atom extract a little bit of information. At the start of the experiment, we inject a small microwave, classical microwave field in the cavity. We don't know how many photons there are in, so the histogram is flat. The probability of having from 0 to 7 photons is uniform. And as you will see, the computer which is hooked to the experiment will show that this probability, as you acquire information, changes in time. And after a few tens of atoms have crossed the cavity, 1 photon number suddenly emerges and survives. Here, 5 photons. And we were very excited when we saw this for the first time, because this is under your eyes the collapse of the wave function. You start with a system which is in a superposition of photon number states, and in the end, by the way of acquiring information, the system collapses into a given number. These experiments, of course, emphasize the particle aspect of light. As I told you before, maybe first I should add something. We could follow on a longer time scale what happens to the field once it has been prepared in a Fock state. And you see here the quantum jumps of a field initially containing 4 or 7 photons. And very recently, we are able to do something more than that, not only to observe the field, but to react back on the field and to preserve the field into a given photon number. You see here that we can stabilize the field either in a state containing 4 photons or 7 photons. This is called quantum feedback because it is an extension to quantum systems of the classical feedback method which are used to stabilize a classical quantity. You just you observe and correct for changes. Here we correct for changes, for instance, by injecting 1 photon or subtracting 1 photon on demand. But as I just said, we want now to explore the wave nature of this photon in the cavity. And this duality between wave and particles is, of course, one of the deepest aspects of quantum theory, and Bohr emphasized the point that which aspect is observed depends upon the kind of experiment you are doing. And this is a metaphor here. If you can read this ambigram either as light is a wave or as light is a particle, depending upon your state of mind. So I want now, and this ambigram has been drawn by Douglas Hofstadter. What I want you now to get into the frame of mind telling that light is a wave. And this will lead us to the discussion of Schrödinger's cat. I remind you the story, and you know it. You have a big object, an animal in a box, an atom in a linear superposition of 2 states. One state leaves the animal alive, and the other state triggers a contraption which kills the animal. And if you are halfway between the excited and the lower state, you get an entangled superposition with a cat which is half dead and half alive in a quantum superposition. In our version of the experiment, we still have one atom, but we replace this cat not because we don't want to make a cruel experiment, but because we cannot do it on a large system. We replace it by a system made of a few photons. And to understand that, I have to give you just one piece of theory here. A classical field, a field which has a well-defined phase and amplitude, which is produced by a classical source, is a classically a point in phase space. It's a complex number which has an amplitude and a direction. According to quantum laws, it cannot be a point. You have quantum uncertainty, and in fact, it's a fuzzy ball here, which has a Gaussian distribution. This Gaussian distribution contains all the information you want to have about the field. Technically, it's called a Wigner function. It's a 2D real function which describes the state of the field. So you can prepare these states very easily. And then by sending Rydberg atoms through the cavity, you can manipulate this Wigner function into other shapes. And one thing we did 20 years ago with our colleagues, Luis Davidovich and Nissim Zaguri from Brazil, was to find out that the same setup which was used to measure non-destructively the photons could be used with a single atom to prepare a Schrödinger cat state, a superposition of two fields of opposite phase. One would be the live cat, the other one the dead cat, and in between, fringes which describe the superposition. This kind of situation is quite different from a statistical mixture, the fact that you have a live or a dead cat, you don't know which, but without this superposition. This is a classical state, and this is a quantum state. So we described in this paper how to build these quantum states, and in fact, we are able to do it in a very simple way. It's again our Ramsey interferometer. We start by preparing a field in the cavity. Then we send a single atom, prepare it in a superposition of state. This atom crosses the cavity, and it imparts to the field a phase shift, which takes opposite signs depending upon whether the atom is in the upper or in the lower state. So you get at this point an entangled state. This entangled state is a typical Schrödinger cat situation, and you can also look at it as a typical measurement situation. This state is a kind of meter which points in different directions, happens in all measurements. So you get an entanglement in the measurement. And then the atom crosses the second zone, and the second zone mixes the states again, which maintains the cat's ambiguity. And in the end, when you detect the atom in one state or the other, you project the field into a cat. So I don't have time to enter into the details, but we can reconstruct the Wigner function of this cat by sending subsequent atoms across the cavity by a modified version of the QND measurement and repeating the measurement many, many times and many, many copies. We can reconstruct the Schrödinger cat, and this is an experimental cat. You see the two bumps which represent the live and dead animal, and also the quantum interferences in between. This cat has about 2.5 photons on average, and since then we have made slightly larger cats, but you see we are still very far from having a macroscopic system. Furthermore, these superpositions are very fragile. The coupling to the environment washes out these features and transforms the cat very quickly into a mundane state mixture. The people, the person who described the theory and the role of the environment in the transformation of the cat from a superposition into a mixture is Wojciech Zurek from Los Alamos, and we were inspired by his theoretical work to do our experiments. And you see here that you can indeed see how the Wigner function evolves by taking snapshots of these Wigner functions at increasing times, and you see how the cat evaporates, how the quantum nature of the cat evaporates with time. This experiment can be seen as an exploration of the boundary between the quantum world, where quantum state superposition exists, and the classical world. An earlier version of the experiment done 15 years ago with a cavity which was not as good had already revealed that the coherence of the cat decays, and it decays faster when the distance between the two states of the superposition is increased. I think at this point, I want to conclude by making some connections with more recent developments. Here I'm talking about Rydberg atoms and microwaves in superconducting cavities, but you have had also very beautiful experiments which started in the 1980s in the optical domain. The cavity is then much smaller, dielectric mirrors, and cold atoms cross the cavity, and the interaction of these cold atoms with these optical cavities or microchips has led to very interesting experiments, the pioneers being Kimball in Caltech and Gerd Rampe in Munich. In other developments, you can replace the cavities by the evanescent field in a whispering gallery mode of a microsphere or a microtoroid, and again, beautiful experiments have been done. In solid-state physics, you can embed quantum dots between Bragg layers, and again get cavity QED going on. And last but not least, there have been a very important development lately called circuit QED, in which artificial atoms, which are small circuits with Josephson junctions, are coupled to coplanar lines or 3D photon boxes in the radio frequency domain. And these systems, which are now studied in many laboratories in the world, are very similar to our microwave cavity experiments. And in fact, a lot of beautiful experiments preparing Fock states, Schrödinger cat states, or doing quantum informations are now being developed with this system in circuit QED. I just give you an example. This is our cat in cavity QED, and this is a similar cat obtained at Yale University this year. You see that you have exactly the same kind of physics. The difference is that in circuit QED, things go much faster, so you can accumulate data faster, and also you can maybe integrate better the two-level systems together, because you can use lithographic techniques which are very convenient. And so this is a very, maybe a very useful device for quantum information. But I leave the discussion about quantum information to Dave Wineland. I want now to make a few personal remarks, if I may, using 2 or 3 minutes for that. I want first to emphasize that all this has been a collective adventure. I have been working, as I already said, for a very long time with Jean-Michel Raymond, and for more than 20 years with Michel Brune, and nothing would have been possible without this long-term collaboration. We directed the group together. We had this long discussion, decided in which direction we wanted to go. We made, Jean-Michel and Michel made many seminal contributions to the understanding of the system, and it's quite clear that it would not have worked without them. So I think they deserve to share the honor of the prize with me on this part of the prize. I also want to say that, of course, we are not alone. We have counted more than 100 people during the last 30 years, students, postdocs, and visitors, and this is the last generation, the people who gathered on October 10th of this year. And I want to mention especially Igor Dotsenko and Sébastien Glaise, 2 young researchers who played a very important role in the last series of experiments that I described to you. I also want to say that all this came also through collaboration with people from outside. And I'm very glad here to see that you have a lot of people with whom we have been working in the world who are around, who are in this room. I think it's a privilege of our profession, it's not a profession, of our passion, to be able to meet people everywhere in the world who share the same ideals, the same wish to find, by just mere curiosity, new things about nature, and this really has nourished us. I want also to finish by talking about the place where this research has been doing, and I want to say that the spirit of freedom, which I enjoyed and which our group enjoyed, comes back to the legacy of Alfred Kastler and Jean Brossel, who created the lab in the 1950s. And you see, this picture was taken exactly in the same room as the previous one, but 46 years earlier, on the day that Alfred Kastler Nobel Prize was announced. As you can see, Claude and I looked different from outside, but I think he agrees that inside, I don't see the difference in our minds. Now, to conclude with even more personal remarks, of course, I have a thought for my parents and for all the people who are no longer here and who have really enjoyed this time. But I want also to add that more than everything else, nothing would have been possible without Claudine, with whom I have shared all these years. And I must say that I don't say if I should say her or you, her mind and her intelligence and her sense of humor have been really fueling me during all these years, and this goes much beyond science and physics. And we have known each other much before I knew anything about photons. In fact, we met when we were very young, and then there was this kind of, I don't know how you call it, an interruption of many years, and the circumstances of life made that we encountered again. At the time I was like this. And if you think that I am young on this picture, what would you say of the next one? This picture was taken in Casablanca in the winter of 1950, and you see at that time Claudine, the only difference that Claudine was as big as I am. But I think she has not changed besides that. And you see also that for some very strange reason, the winter in Casablanca is very mild, but for strange reasons, my parents had dressed me already with the overcoat, which is almost ready for the Stockholm winter. Thank you very much. Thank you.